So today we want to take our study of projectiles to the next level. We've already looked at horizontal projectiles, and we saw that we could break it up into two separate problems. A horizontal problem where the motion has a constant velocity, and a vertical problem where the object accelerates as if it was under the influence of only gravity, so like a free fall problem. Time was the element that linked together the horizontal and the vertical motion. Okay, now we want to launch our projectiles on angles. And we did this in lab, so let's see what we learned. Okay, we saw our graph come out something like this. I first want to point out that if you have a 0-degree angle or a 90-degree angle, your projectile is not going to go any horizontal distance. You'll notice starting at 0, bigger angles create a farther distance up until you hit about 45 degrees. And at that point, bigger angles start to make the distance traveled less. And what you're going to see happen is 45 degrees is the best angle in terms of the farthest distance, and the complementary angles like 40 and 50 or 30 and 60 travel exactly the same distance. Okay, our factors or something about our setup that help determine our values. Two things determine our values. How fast is the velocity when it leaves the launcher, and what is the acceleration due to gravity like? Source of error, if you were here for the live, give a source of error for the live lab. If not, do it for the virtual lab. Limits to your model. So I hope you guys realize that this only works if your projectile is not seriously impeded by air resistance. Our projectiles were very heavy and very small, so there was minimal air resistance on them. Okay, I want to talk to you about variables and signs. Okay, so what I'd like you to do is to set up a chart, delta Y, VI, VF, A, and T. VI and VF are your velocities at the beginning and end of the projectile. Delta Y is your displacement in the vertical direction. This will be positive if it ends at a higher height. This will be negative if it ends at a lower height. And this will be 0 if it ends at the same height that it started, like the soccer ball that started on the ground and ended on the ground. V initial is positive if it starts out moving up, negative if it starts out moving down, and 0 if it was shot horizontally like we had last week. V final is positive if it ends its flight while it was still on the way up, ends its flight on the way down, and ends its flight at the highest possible point. The acceleration is always going to be negative, and the time is always going to be positive. So these are the signs you're going to employ for each of your different scenarios. Okay, let me show you an example problem, and we're actually going to do two. The first one will be a corner kick. We're going to have a person kick the soccer ball, and we're going to try to work out where is that soccer ball going to land, how long is it going to be in the air, and things like that. Okay, so the ball is kicked at a speed of 10 meters per second, and it leaves the ground at an angle of 25 degrees. So if you know how fast it's moving and the angle that it takes off at, we should be able to figure out everything we need to know about the flight of the ball. So what you're going to do is you're going to employ your sines and cosines we learned about before. We're going to say the sine of 25 degrees is equal to the opposite over the hypotenuse. You're going to solve for Vy. You're then going to do the same exact thing, but this time you're going to do it for cosine. And the cosine will get you the x velocity. Once you have those x and y velocities, you're going to put them in the proper spot. So the x velocity, whatever number you get, will go in here. The y velocity will go in on the vertical side. Your delta y, we're going to assume the ball starts and ends on the ground, so we make that 0. And we're on planet Earth, so we're going to make this negative 9.8. Okay, we're then going to try to figure out VF, T, move your T over, and you're going to solve for delta X. All right, so you should know how to finish such problems, okay, that are similar to what we just saw here. So step 1, sine and cosine to get Vy and Vx. Vy goes on the vertical side, Vx goes on the horizontal side. The delta y again was 0 because it starts and ends at the same height. Okay, we're going to do one more, and this time we're going to be looking at a football pass. And we can see that the football leaves Ava's hand 3.2 seconds into the video. We can see the football is caught 5.2 seconds into the video. So we know the ball was in the air for exactly 2 seconds. We can see that the ball was about 1.8 meters off the ground when it was thrown, and about 1.4 meters off the ground when it was caught. What we're going to do with that is put that information into our chart. So this would be negative 0.4, the difference between the starting and ending heights. It ends lower than it starts. Our acceleration, we're going to use negative 9.8, and our time we're going to use 2. Our horizontal distance is about 30 meters. Our time is about 2. So with all this information that we got just from looking at the video, we could figure out that the horizontal speed was about 15 meters per second. We can use our different formulas to find the initial and final speed of the ball. We really care about the initial speed. I think when you work your way through it, you're going to get a speed of around 10 meters per second in the vertical. So then you put them together by having the ball go 15 meters per second horizontally, around 10 meters per second vertically, and then you just complete the triangle to find the actual speed and the angle of the throw. So this is an example of each of the different ways we can attack the problem. In this one, we work backwards to figure out the speed and the angle, and on the corner kick, we started with the speed and the angle, and we figured out how far it's going to go. So hopefully this video is enough to get you started with projectiles on an angle.